In previous discussion, we can control the power by using individual pace control and equidistance pulse control out there. The individual pace control IPC, this was used in the early HVDC projects. The main feature of this scheme is that the firing pulse generation for each pace is nothing but each valve is independent of each other and the firing pulses are rigidly synchronized with commutation voltages. There are two ways in which this can be achieved. First one is constant alpha control. Second one inverse cosine control. In IPC scheme, they having constant alpha control, inverse cosine control. What is constant alpha? That is a delay angle control. So the timing voltages are derived from the converter AC bus via voltage transformer and the 6 gate pulses are generated at nominally identical delay times subsequent to the respective voltage zero crossing. The instant of zero crossing of a particular commutation voltage corresponds to alpha is equal to 0 degrees for that valve. So please see the zero crossing detector, variable delay. VC is a control voltage. This is a gate pulses. So in this, how to generate gate pulses by using zero crossing detector. Second one is inverse cosine control. There is a the six timing voltages obtained as in constant alpha control are each phase shifted by 90 degrees and added separately to a common control voltage V. So this is a 90 degrees phase shift. They have a capacitor and inductor. So every waveform we putting the phase shift. Phase shift. We produce a phase shift for every waveform. So this VC control voltage. This is a zero crossing detector to valve gate. The zero crossing of the sum of two voltages initiates the firing pulses for the particular valve is considered. The delay angle alpha is nominally proportional to the inverse cosine of the control voltage. It also depends on the AC system voltage amplitude and shape. So this is a normal wave, this is a control voltage. So the difference between two waves so creates is a firing instant. This is a firing instant. The main advantage of this scheme is that the average DC voltage across the bridge varies linearly with the control voltage VC. Drawbacks of IPC scheme in individual phase scheme. The major drawbacks of IPC scheme is that the aggravation of the harmonic stability problem that was encountered particularly in system with low short circuit ratios less than 4. The harmonic instability, unlike instability in control system, is a problem that is characterized by magnification of non-characteristic harmonics in steady state. This is mainly due to the fact that any distortion in the system voltage leads to in the zero crossing which affect the instant of firing pulses in IPC scheme. The problem of harmonic instability can be overcome by the following measures. First one, through the provision of synchronous condenser or additional filters for filtering out non-characteristic harmonics. Use of filters in control circuits to filter out non-characteristic harmonics in the commutation voltages. The use of firing angle control independent of the zero crossing of the AC voltages. This is the most attractive solution and leads to the equidistant pulse firing scheme. Equidistant pulse control. The firing pulses are generated in steady state at equal intervals of 1 by Pf through a ring counter. This control scheme uses a phase locked oscillator to generate the firing pulses. There are three variations of the EPC scheme. First one, pulse frequency control. Second one, pulse period control. Third one, pulse phase control. Pulse frequency control PFC. A voltage controlled oscillator VCO is used, the frequency of which is determined by the control voltage VC, which is related to the error in the quantity, that is a current, extinction angle or DC voltage being regulated. The frequency in steady state operation is equal to Pf naught, where F naught is the nominal frequency of the AC system. PFC system has an integral characteristic and has to be used along with feedback control system for stabilization. The voltage controlled oscillator VCO consists of an integrator, comparator and pulse generator. So please see the voltage control oscillator consists of integrator of time Tn minus 1 to Tn constant K1. This is a comparator with compare with V3 with integrator output. This is a pulse generator. This is a ring counter. Here there is a control voltage and normal operated voltage. So the voltage control oscillator consists of integrator, comparator and pulse generator. The output pulses of generator drive the firing counter and also reset the integrator. The instant Tn of the firing pulses is determined by integral Tn minus 1 to Tn K1 Vc plus V1 of dt. Control voltage and V1 voltage is gives the V3 voltage in diagram. Please observe the diagram. This V3 will be derived by using this circuit, where V1 is a bias constant voltage and V3 is proportional to the system period. In steady state, Vc is equal to 0, and from the above equation we get K1 V1 of Tn minus 1 is equal to V3. Since Tn minus 1 is equal to 1 by Pf naught. In steady state, the margin K1 of the integrator is chosen as K1 is equal to Pf naught V3 by V1. The circuit does not incorporate frequency correction. When the system frequency deviates from F naught, the frequency correction is obtained by deriving V3 as V3 is equal to V2 by 1 plus ST1. V2 is equal to K1 V1 of Tn minus 1 to minus Tn minus 2. So from pulse generator, so this is a V1 sample and hold circuit. This is a 1 by 1 plus ST1 will give the V3 voltage. Pulse, second one is a pulse period control. It is similar to PFC except for the way in which the control voltage VC is handled. The structure of the controller is the same. However, VC is now summed with V3 instead of V1. Thus, the instant Tn of the pulse generation is K1 V1 dt integral Tn minus 1 to Tn is equal to V3 plus Vc. K1 V1 of Tn minus 1 is equal to V3 plus Vc. With Vc is equal to 0, the interval between consecutive pulses in steady state is exactly equal to 1 by Pf naught. Please see the timing diagram. This is a pulse, this is a reference, this is a pulse. By using this one, we generated pulses. Pulse space control. An analog circuit is configured to generate firing pulses according to the following equations. Integral Tn minus 1 to Tn K1 V1 dt is equal to Vcn minus Vc of n minus 1 plus V3, where Vcn and Vc of n minus 1 are the control voltages at the instant Tn and Tn minus 1 respectively. For proportional current control, the steady state can be reached when the error of Vc is constant. The major advantages claimed for PPC, pulse space control, over PFC, pulse frequency control, are easy inclusion of alpha limits by limiting Vc as in IPC, and linearization of control characteristics by including an inverse cosine function block after the current controller. Limits can also be incorporated into PFC or pulse period control system. Drawbacks of EPC scheme. EPC scheme has replaced IPC scheme in modern HVDC projects. It has certain limitations which are: under balanced voltage condition, EPC results in less DC voltage compared to IPC. Unbalance in the voltage results from single phase to ground faults in the AC system, which may persist for over 10 cycles due to stuck breakers. Under such conditions, it is desirable to maximize DC power transferred in the link, which calls for IPC. EPC scheme also result in higher negative damping contribution to oscillation when HVDC is the major transmission link from a thermal station. Current and extinction angle control. The current control is invariably feedback type, which is of PI type. Please see, this is a current actual, current reference. So based on this one, we generate the control voltage. The extinction angle controller can be of predictive type or feedback type. With IPC control, the predictive controller is considered to be less prone to commutation failure and was used in early schemes. The feedback control with PFC type of equidistant pulse control overcomes the problems associated with IPC. The extinction angle as opposed to current is a discrete variable, and it was felt the feedback controller of gamma is slower than the predictive type. The firing pulse generation is based on the following equation. 0 is equal to integral minus pi del n minus 1 to omega Tn Ecj d of omega t plus 2 xcid, where Ecj is the commutation voltage across the valve J and Tn is the instant of its firing. In general, the prediction of firing angle is based on the equation Bj is equal to gamma reference plus mu j, where mu j is the overlap angle of valve J, which is to be predicted based on the current knowledge of the commutation voltage and DC current. Under large disturbances such as sudden dip in the AC voltage, signals derived from the derivative of voltage or DC current at the advancing of delay angle for fast recovery from commutation failures.